So hello everyone. This is the video to introduction to openFoam. In this video, we will discuss about the introduction to openFoam, which is an open source software, which in which the FEM approach is taken place. In this video, we will discuss out the problem of the flow past a 2D body, in which the 2D body is the ellipse along its minor axis. Flow will take place on the ellipse throughout its minor axis. It is the external flow problem. As we know, the external and internal flow are the categories in the flow problem, in which the internal flows have some boundaries. In the external flows, boundaries are not there. The boundary layer formation will be there above the streamlines. Stream velocity will be there. Means the in the stream velocity, the flow will be taking place. It is just needed to the aerodynamics of the objects. It is these problems are discussed in the external flows of the vehicle and other obstacles. Aerodynamics study of the vehicles also takes place in this problem, in which the lift drag means the how much air should be there, so drag will be there, how much drag will be there, and how much lift will be take place by this much of velocity of the stream velocity. In this we will discuss a problem setup, which is considered here. The incompressible flow is there, and the rectangular domain of 15 into 10 units will be there. Obstacle will be ellipse, whose center is 2.5 into 5, 2.5 in x-axis, 5 in y-axis. Major axis will be 2 units, and minor axis will be 1 unit. Bounding conditions at the walls of the ellipse will be u equal to 0, and the pressure outlet will be p equal to 0. For the 2D model description, this blue one here is the inlet section, and red one is the outlet section. At the walls, boundary conditions considered to be no slip condition at both top and bottom. And for the inlet section, for the x velocity, u will be equal to 1 meter per second, and meter per second, or any unit per second. Okay, b is in the direction of y velocity, which is considered here the 0. And as the this boundary condition is Dirichlet, so Newman condition for the pressure will be there at the inlet. For the outlet condition, we consider the pressure outlet equal to 0, and as we have pressure outlet is equal to 0, then it will be the 0 gradient condition for the velocity. That is vice versa. That is velocity will be Newman. As we see here, for the dimensions, 10 will be 10 units will be in the y direction, and 15 units in the x direction. And ellipse, which is considered to be 2.5 units from the x-axis, and the y-axis its center will be 5 units, and major axis will be 2 units, and 1 will be the minor axis. Okay, solver here consider in openFoam inbuilt solver, that is icofoam, which is specially designed for the incompressible laminar flow. Boundary conditions compatibility for this solver is the velocity inlet is considered, no slip. Walls is also considered, pressure outlet is also considered. So we are considering here the solver icofoam, which is most suitable one for our problem. So if now we will go for the openFoam part, practical part. In the as I have installed the VMware, means the VirtualBox for the Ubuntu machine for the playing of the openFoam. So first of all, we make a folder for the our assignment problem. So for the folder, we can see is where we are, that pwd command. We are in home section, so we will make a folder of uh, openFoam assignment. So we will go into this folder. So it is empty. In this we will make the geometry folder now. Mkdir geometry. We will consider the whole geometry in the separate folder. So then we will run into geometry folder. So ls, this folder is empty one. Then here we will make a file of gmesh, that is gmesh ellipse ellipse.go. Then our gmesh will be open. For making geometry, we will go into the geometry, then elementary modules, then add. For adding the geometry, we will consider firstly the points. These are the point sections, and firstly we consider the 0, then 0. This will be origin. In the 50, we have seen in the x direction that first domain will be 15 units and 0 will be the x, then second point will be there, and these are the points that we are going to take for the our simulations. Then next point will be uh, x direction, that is 15. For the y direction, this is 10, and add, and fourth point will be 0 for the x direction, and for the y direction it will be 10. These are the 4 points for the rectangular cross section. Now we have to make the line from these points. So we will consider first that select end point, then we have to select the end point, then line will be forming, and it is saying the start point, then start point will be there like this. We have to do whole the geometry, and this will be the start one, and this is same one, so I am doing fast forward. After this, the line part, we have to make the ellipse part. So ellipse part is 2.5 from the 2.5 from the x direction, and from y direction from the origin it will be 5. Then 2 point, we have to take 2.5 for x and 5 for y. That will be the point. And after this, second point will be that the one will be the minor axis, so we have to decrease in y axis 1 point. Yes, in this way one, then we have to increase x to 2.5 plus zero point 0.5, that will be 1, means 2.5 plus 3. Okay, add. Now for the y direction, 2 will be the x direction, and in y direction it will be 2 units. Then we have to take 6 will be the y direction. Oh, sorry, 2 and 6 will be in y direction. Then, oh sorry, 0.5, and in the y direction 6 will be there, and add, and 2.5 in the x direction, 4 will be the y direction. These are the 5 points from which we are making ellipse. From the ellipse arc option, we can make this ellipse. It is saying what is your start point, and start point is this, and it is saying about the center is this one, and next one is major axis, means the major axis for this is this one. Then we will consider the this point, and the end point will be this one for us. So in this way, four arc will be considered and the whole ellipse will make. And I am doing fast forward. In this way we can make the ellipse from the ellipse arc. After this, we have making the 2D domain from this, as openFoam is considering always the 3D one. So in the y direction, we have to consider the one in the z direction. So in the z direction, I will be opting this as the one unit for this. Okay, after this we have to make the surface of the whole geometry, and plane surface is there. We have to take the surface boundary is this, and we have to select whole boundary is the ellipse one here. It will subtract the surface from the whole surface from the throughout the whole surface. Okay, means the ellipse part is subtract out from the whole domain of the body. So we consider E is the command for the end selection. Then, okay, then the surface is, we can see all the commands in the edit script option. This script is forming by taking this each and every state. So the plane surface we have making here is 1 is 2. By this we can go now for the for extrude is the surface we are taking in the z direction. So we can see here for the z direction, we can say in the z direction one unit will be only taken, as it is the 2D problem. So I am taking the in the z direction 1 unit only, as it is compulsory for the open form part, so it will be needed. Okay, so For this I will consider the surface. Okay, then uh, E will be for the end selection, then E will be end. Okay, after this we can see it is implementing on the script or not. The script is opening, load, and extrude surface. For the extrude surface, one two command is important, that layers one. And I don't know the actual reason for this, but after extruding we have to do this. Okay, we combine, then save. We can load our script from the reload option, reload script option. From this we have reloaded. And then after this we have to make the mesh. This is the geometry part. For the mesh part we have to go in the mesh. First is the 1D, then 2D, and then 3D mesh. 3D mesh will be there for this, like this. Q will be the end selection, and like this we can do mesh along this. As it is course one, so we will consider at the walls of the ellipse I want the denser mesh, so I will consider the denser mesh from these domains. I can do it by saying point, or I can change the code in the script that this part is last one part 1.0 1.0, it is for the mesh space grading. So I will change it from the script at 1.0. I will consider as 0.1 as I want the denser mesh for the ellipse point, that is 0.1. 0.1 I'm doing the fast forward. Okay, and 0.6 for, as I want the whole domain to be uh, good results, and I am considering here the also a little bit denser mesh for this, so I am considering the 0.6 for this. Okay, 0.6. Then we have to save this and implement this in the gmesh, that where is reload script. After this we have to go in the 2D. As we can see the denser mesh is appearing throughout the whole domain, and uh, in the ellipse part it is the denser more. Control alt plus click is for the resetting of the state in the gmesh. Now we have to make the inlet section. Outlet section means the naming is compulsory for this. After this we have to take one, this one part is inlet, this part outlet, then top boundary and the bottom boundary. So for the naming we have to go in the physical groups, then add, then surface. Firstly we will take here the inlet part, and the inlet will be this one, so E will be for the end selection. And next one is outlet. outlet Outlet is for this part, then E will be the end selection. And next one is top top is for this one is end selection. And after this bottom, blue one is showing that this part has named, and bottom, then E, then blue part is showing here. Then this means that the selection is done. And this open form is needed, front and back portion, then front and back, front back back portion. So front will be this, and this, as it is 2D domain, so front as back is not needed so much, and the front and back will be this. Okay, then E will be for the end selection. Then next one is ellipse part, as ellipse is also body. Then for the ellipse we have making the ellipse by 4 points. Then we have to, so we have to select all the 4 points. These are the ellipse one for this end selection E. Okay, now blue point has done, and for the surface part is done. For this the surface part is done. And next one is the volume, sorry, volume from the physical groups. Then whole volume will be of fluid. E will be for the end selection. Okay, as we can see in the script that the physical surface has been carried out for all the naming convention. Now naming convention is done. We have to save this geometry, this mesh for the open form. So for the open form we have to export this in to ASCII format. So ellipse dot msh will be the extension for the mesh from this we opt the .msh extension, then we will save. Okay, we have to save this in ASCII format 2 version 2, as openfoam supports only the ASCII format of version 2. Okay, then we have to apply this. Okay, after this the mesh has been saved now, so we have to go in the terminal. As we can see, we have to close now gmesh, and ls will be the command, ls. So we can see here the ellipse.msh is there. For the open form, we will consider a case of tut will be the command for the tutorials of the open form. We will consider the cavity example tutorial from the open form pre default one. We have to go in the incompressible folder here, then ll, then we have to go in the icofoam, and then ll, then cd cavity. Yes, for from here we have to copy the cavity folder in the open form assignment folder. Okay, so now from the cavity folder we can copy this wise cp minus r uh, folder cavity cavity, then we have to uh, copy this in the assignment folder, then it is in the home Monday, then open assignment, then we have to copy this and paste. Actually there is no cavity folder, so I can do one thing, that I will cd dot, then I will copy this. Okay, yes, then this is copy. We can copy this by GUI also. This is the open form assignment. So we have copied this by GUI. This is the cavity case here of the open form. Yes, for the open form, now we have to do one thing. Firstly, in the constant folder, we have to copy this outside this folder, as in the open form we needed 0 constant and system. But for the gmesh, to change the gmesh geometry for the open form, constant folder is not needed firstly, so we have to delete this. Okay, first delete this, then go to the terminal in this folder, then write first of all copy the mesh file from the geometry folder in this folder, cavity folder. Now go to the terminal, then write a command gmesh to foam, then file name at ellipse.msh. Yes, from here and is showing that mesh has been set to the open form. We can see now the constant folder here and the polymesh, then the boundaries we can see, we have named all the boundaries here like this. We can play the different geometries dimensions from the gmesh to open form. After this we can see here in the boundary folder, type patch is for all the naming conventions here. So we have to do one thing. For the front and back we have to do this empty, as it is 1D domain, means 2D domain. So top is here considered to the physical type, patch is for the inlet where the flow is taking place. Okay, for the walls we will consider walls only. Okay, wall inlet will be the patch, as we are considering u velocity for this. So in the other part, bottom will be wall part, outlet it will be also the patch one, and this should also, ellipse should also the walls part. Yes, by this save, then go to this folder boundary. Now the file physical properties, in which the new will be there. New is here the kinematic viscosity, then we have to copy this again into the constant folder. Then after this we have to do one thing, check mesh is okay, then we have to consider the boundary conditions for the 0 folder, that the pressure domain means the pressure condition boundary condition and the velocity boundary conditions for all the boundaries. So for pressure. As we open the ads, it is for the cavity domain files that we have copied from the tutorial folder. For our case, we have to make all the boundary conditions uh, by our naming. Okay, so for this I will copy this from the boundary folder, then go into the pressure folder. Then for the reference, I am considering this only here now. After this, for the front and back, we can consider this empty, type empty. For the top, as it is ball, for the fixed ball, pressure condition will be means the u will be equal to 0. Then we have to take the 0 gradient for that. Okay, type 0 gradient, we will copy from that. And for the top, it will be 0 gradient. Bottom will be also u equal to 0. Then we will consider the ball also the type 0 gradient. Outlet balls will be ellipse will be also ball. Then for this we will also consider grade 0 gradient. Outlet will be the pressure outlet, so we will consider for the inlet and outlet some values, fixed value for the inlet pressure conditions. For the inlet section here, type will be considered as the 0 gradient because u is considering I have the Dirichlet condition, boundary condition, so type will be the 0 gradient. Hence I can copy the whole equal to type 0 gradient. After this, the outlet is pressure equal to 0, that the Dirichlet condition will be for the pressure, so type here will be fixed value, and the uniform value will be equal to uniform 0. Now we have to save it, and we have to make changes for the u folder. That u folder, for the u folder velocity one, I will copy this from the pressure folder. Sorry, for the pressure folder, for the previous case I have not cut out the moving wall, fixed wall and front wall option, so we have to delete, as we have not this type of naming convention, so we have to delete this. And for u, we have to copy this one into the u folder. By the way, this one is the dimension for the pressure conditions, means the pressure units will be the in the mlt units will be like this. And for the velocity, we make changes like this. First of all, save this file for the pressure. Then for the u, in the front and back, we have to take this for the empty, and top will be no slip, as it is wall u equal to 0. Inlet will be some value. Bottom will be also no slip, and ellipse is also wall, then no slip will be there, no slip, there will be no space. For the outlet, as for the inlet, some value will be there. For the inlet, fixed value, then value equal to value is equal to uniform, as it is in the x direction only, and 1 0 0 will be there. We have to make this colon. After this, for the outlet, we have to do the 0 gradient for this, as this is pressure Dirichlet condition, so we have to make this 0 gradient, which is Newman. After this saving of the u folder, we have to delete the previous u folder values, that front, back, moving wall and fixed wall, as this is not our naming conventions. So save it, and after this, go to in this folder u, then go to in system, then the control will be the folder in which the solver will be take place and the start time will be take place. First of all, we will run from this time steps only for the openFoam, because we have to test first what is running or what is not. Then we can go by this terminal, then write it check mesh command. Yes, this is showing that the mesh is okay, so we can proceed for the solver. Then we can run solver by openFoam Hope all the condition would be good. Yes, it is running. We can see this by the parafoam command. Okay, something is wrong. So it is making the temporary cavity dot open form. This is the paraview which is used for the post processing of the open form. Then apply cavity dot open form. This will be this is the domain we have to do the analysis on that. After this, we can see the u part is here. We can see the velocity by applying for the 0 timestamp. We can see it is running or not. Yes, we can see that some weights are displacing, so we can see here yes, velocity is having some changes. We have to make changes as there is only the 5 time steps, so we have to change make the changes in the control dict folder. So go to in the control dict, we have to make simulation up to 50 seconds for showing some good output, then 20 will be the writing interval. So after this we have to save this. Yes, save this, and we have to delete this folder. After this, save and go to in this folder and close the paraview. After this, go to openFoam command. Now this is running. As it is not compiling, we can see here the compiling fast. We can see 6.1 6.77 seconds. It is here up to the 12 seconds. So we can see the real-time data also in running simulation by opening another terminal. Just open terminal in this folder, open terminal, and do the parafoam command. By parafoam we can run the cavity.openFoam file. So apply, and after this we can see the u velocity variation with time. It is appearing in the parabolic profile. We can see the vector profiles by taking the ellipse, and for the ellipse we have to take orientation should be u, and some small scaling factor should be there. So apply and apply. We can see the vector flows by these commands, then play. Yes, that's how the flow is taking place. We can see here, we can zoom this by our mouse scroll. We can see how the flow is taking place. There is vortices taking place after the ellipse body when the flow is flowing from inlet to outlet. You can see some eddies are taking place here. Arrows are showing. We can see the different results by the vector representation here. We can see also the how the flow is taking place outside the domain. These arrows are showing. We can dance this also by increasing the scaling factor. Just we have to increase the scale factor, and after this we have to apply. So that's how you can see the different eddies formations. You can see the it is up to the 20 seconds. 20 means for the 21 seconds how the fluid is, what is the fluid state. So we can see this from here. By this way we can see the how the flow is taking place inside the fluid domain by an obstacle, that is ellipse, we considered here. We can see the vector errors also. You some factor will be there, then apply. This is how the vortices will be forming, how the vortex is forming. We can see by the streamline here how the vortex is forming. The simulation is for the 50 seconds. For this we can also see the drag and lift coefficient frequencies from this software by implementing some codes into the control dict folder, from where we find some values in the log folder, means the log file, and compile it from the Python. Okay, so for compiling it in the Python, we have to go in the constant folder, sorry, in the system folder where control dict folder is there. Then we have to make changes. After the runtime, we have to paste some codes like this for the forces and the force coefficients in which the lift drag is there. Then we have to run this simulation again. Without something to tell that in the control dict folder we have to specify ellipse on which the forces is taking place. So patches name is here ellipse. We can find this code from the openFoam help. So ellipse will be there. After this we have to run icofoam. So simulation has been started. We have to wait for some time. uh, as we can see, some post-processing folder is there. It will contain some value after the calculations up to the 50 seconds. uh, and these are some files: plots.py and the stool.py. Plots.py define the drag coefficient and the lift coefficient, how much frequency this is taking place. This code simply load the text file from the post processing file, then it will implement the code on that. Okay. uh, for the stool, how much vortex at bit at what hertz of frequency the vortex has been made out, or something vortex is occurring. So stool number tell us that how much frequency is of the vortex is there when this kind of obstacle is taking place. So if you see, the simulation has been carried out to 50 seconds. So forces, sum of movements, some values are there, force coefficients. Now we can see the results by the some Python scripts. We can see our Python scripts are uh, plots.py and stool.py. First of all, plots. What is this? Python plots.py. It is it can be seen here that the drag coefficient is the blue one and the lift coefficient is the red one. By this, the lift has been carried out after 50 seconds more, and drag is somehow increasing, and after that the fluctuating one. After the 40 seconds it is fluctuating one. And if we see the stool number, for the stool name, same command python dot stool. So we can see the 0.04 hertz frequency is there. 0.07 up to 7, I think so, 7 hertz frequency is there of the vortex. We can see by the vortex shading frequency 0.078 hertz frequencies of the vortex. In this way you can compile the projects in openFoam by parafoam command. You can see the different outputs by different values like this. We can see the velocity at the outlet like this kind of contour is uh, making out after the 50 seconds. We can also show ellipse for that. Yes, ellipse is like this. Some, if we carry down slow, then apply, like in this way vortices are happening. So in this way you can perform the simple openFoam basic tutorial. So thank you.